So we will look at some review questions from the book today. Uh, so the questions are here. You can use. Are you going to use the same thing to answer? Write down the answers. Okay, some questions are pretty easy. Some are a little bit thick, but most of them are pretty easy. Right, so this is nothing unusual. True or false? If something has probability 1000%, is it sure to happen?
And then the statement is false.
Yeah, statement cannot be correct. Yeah, and there cannot be 1000%. So therefore it's false. Second one,
Something has problem.
if something has probability 90%, actually as I mentioned at the beginning, it's wrong to say probability is 0.9. Maybe you can say chance, but anyway, this book is always talking about probability as a percentage, which is really wrong. Because probability has to be between 0 and 1 always. 90% is not 0.9. If something has probability 90%, it can be expected to happen about 9 times as often as opposite. Is that correct?
Yes.
Yeah. That's correct. So next few questions are related to the deck of cards. I'm not pretty sure. I mean, I sometimes forget what these cards are. Very long time ago I played, maybe, but now I forget. That's why I got some. But probably maybe you are familiar with that. Right. So let's look at this. Two cards will be dealt off the top of a well shuffled deck. You have a choice to win $1 if the first card is a king, or to win $1 if the first is a king and the second is a queen. Which option is better? Are they equivalent or expensive?
Mm, So the second option is better, I think, because the getting the chance. There are 52 cards now, so there are four kings. So
First one you get $1 if you get a king.
yeah,
Right. Second one you get $1 if the first is a king and the second is a queen.
yeah. So if the first one was meaning the first chance is 4 out of 52.
Second one can be anything, no?
Yeah,
Yes.
yeah. So, I was thinking about logic actually, that's the implication.
Was it?
I was actually thinking about logic. So if the first state, so it says if the first is a king, no?
Yeah.
So if it
And
doesn't,
the
the
question
statement.
says two cards will be dealt, so anyways we are going to take. But if the first one is a king, you get $1. The second one, first one has to be a king, and second one must be a queen also.
So,
So which one is better option? Better chance of winning $1? High probability. First one is a king. What is the probability? How many kings are there?
four,
Four. So 4
4
out of 52. Second one can be anything, no? Right. So there are how many chances? Once you take one, there are 51 more. Anything out of 51 can be for the second. Right. So the probability, if you calculate the probability, is going to be 1 over 52 times 51 over, sorry, 50 over 51. Right. It's coming from the conditional probability. So for the second one, first one is still a king 1 over 4 over 52 times. Second one must be a queen.
yeah, 4.
So it has less chance, right? So therefore, if you multiply, the second one will have a smaller probability, a smaller value. Okay? You can just think, right, because the first one has to be a king. In both, first one has to be a king. This second one,
Yeah.
anything can happen, right? But here it's restricted, so the probability is small now. So therefore, the first one has a higher chance, right? So if you calculate the probability, is going to be like this. Which rule has been used here? Uh, Here, just multiplying some two values, right? Which rule has been used there?
Independent.
Yeah, no, actually not independent. Right? We are using the multiplication rule. Probability A intersection B, we want A and B both to happen. Right? If A and B are independent, we can say this is equal to probability A times probability B. Right? But even though it looks like this one, this is not the one that is being applied here. This is a special case, no? This is a special case if A and B are independent. But here we have actually applied the general case. The probability A or B given A times probability. Right? Because once you've taken one card out, the second result depend on the first result. So they are not independent. So therefore you have to apply the general rule here. Right? So the first one being a king is this one. And given that it is a king, the second one is this one. Coming out of 51. Right? So it's not the independence, but it's the product rule anyway, the general rule. Product rule. Right. Four cards will be dealt off top of well shuffled deck. There are two options. To win $1 if the first card is a club and the second is a diamond and the third is a heart and the fourth is a spade. So that is an order also. And all four types have to be there. The second one, to win $1 if four cards are of different suits in any order, right? So in that case, we don't say first one, second one, third one, so it can be any order. So which one has high chance? Second. So what is the probability of the first one? Meaning first one is a club and the second one is a diamond and the third one. Which rule shall we apply there?
The conditional probability.
Conditional probability again, yeah. You just extend it to four events. Yeah. So it's like probability of A given B times yeah. B need A intersection B intersection C intersection D. So this is probability of A given B. Normally say you have to give probability. Let's say D given A and B and C times probability C given C intersection D given A and B, like that, right? They have to be cancelled out also. The last one is D given A and B and C has happened times. So first of all, this is going to be like this. So this one we can write down again probability A given B given probability B given C times probability of A given A times probability of A, right? If I write down in the equation, right? So D given A, B and C, and then happen times that, and then this is equal to probability B intersection C given A and B times probability of A and B, right? And this one can be written as probability B given A times probability of A. So it's like probability of D given A, B, C times probability C given A and B times probability B given A times probability of A. That's how it comes. Minus D times this one, so that one is equal to probability of C given A and B times probability of A and B. This D can be written as probability B given A times probability. Right. Okay. Okay, let's look at this one. A poker hand is dealt. Find the chance that the first four cards are aces and the fifth one is a king. Okay, can you calculate it? First four cards are aces. The fifth one is a king.
4 into 3 into 2 into 4.
4 into 3 into 2 into
4 divided by 52.
4 into 3 into 2 into again 4 you said or 1?
1 still
Yeah.
makes no sense. Again, then 4
Again 4. Okay.
divided by 52 into 51 into up till 48
52
into 51 into
yeah.
up to 48.
We are taking 5.
The 50 second.
52, 50, yeah, no. How is happening? No. 52 we have cards, ne? We are taking how many cards?
5.
5 cards. Yeah. That's correct. One ticket will be drawn at random from the box. Are the color and the number independent? Can look at it in different ways. For example, if the color and number are independent, what do you expect to happen? Right? The color is only white or black, right? Number is 108, right? So let me denote the color by C and the number by N, right? So if they are independent, what you should have probability that C is equal to some color like that. This C can be white or black, right? So color can be white or black. Number can be 1 and 8. Right? So if C and N are independent, this intersection N is equal to some number N should be equal to probability C is equal to C times probability N is equal to N. That is one way to look at. So that should be correct for all possible combinations of C and N, right? If these two events are independent, right? So, or you can look at this way: if they are independent, then the probability, for example, probability of a given number N is equal to N, given that color is equal to some color, should be the same as the unconditional probability of N equal to N. Right. So this should be true for all C plus C and simple n also, right? So that is another way to look at it. Oh, general understanding is what we can look at is, for example, if you look at the distribution of numbers given the color, right? Say for example, if color is white, the distribution of the numbers is probability that the number is equal to is 1 over 3. Probability that the number is 8 is just 1, the number is equal to 1 is 2 over 3. Number is equal to 8 is 1 over 3. So that is only two numbers. One probability is 2 over 3, the other probability is 1 over 8 if the color is white. If the color is black, still the same. So the two distributions of the number doesn't depend on the color, if they are the same. So that is the easiest way to understand. This is just mathematics, no, you have to have it, but to understand, you can just look at the distribution. It's very easy because only few numbers. So given the color, distribution of the numbers are the same. So therefore, that means they are independent. If the distribution was different with the color, then we say color and number are dependent. Right? So you can look at it these three ways. Right? Deck of cards is shuffled, and top two cards are placed face down table, true or false. There's a chance in 1 over 52 for the first card to be ace of clubs. There is a chance of 52, 1 in 52 for the second card to be the ace of diamonds. The chance of getting the ace of clubs and then ace of diamonds is 1 over 52 times 1 over 52. True or false? The first one?
True.
True. Second one?
True.
Why do you say it's true?
Because you have still opened the first card.
Yeah, that's right. So still, when you take like that, for anyone to be the same chance, you can actually show that using the conditional probability. You can whatever the you can look at, for example, the probability that the second one is a diamond. You can look at looking by using the total probability law also. Right? The second one is determinant to be a ace of diamonds. Right? So if you say ace of diamonds, the second card is ace of diamond. If I denote ace of diamond by AC, right? I want the second card to be ace of diamond. So I want the probability of this event. If you look at the probability of this event, I can write down this thing using the total probability law by conditioning on the first one if I want. Right? If I want to calculate the probability and show that the second it has the same probability. So I can write down this as AC2, that is the second one is the ace of clubs. For example, you can look at another event. You can say, for example, first one is ace of club times probability. The first one is ace of club plus the probability that the second one is ace of club, given the first one is not ace of club, times probability ace of club. So you can look at, if you want to prove it, you can look at that probability. Total probability. So the first one is ace of club or ace of club dash. So that those are two mutually and exclusive and exhaustive events. And then you can look at AC2 event. The second one is AC2 in general. The picture will be like this. Second one is this. So if you apply the total probability law, you can write down like this. But then if the first one is ace of club, second one cannot be ace of club, so this part will be 0. So the probability is only coming from this part. So if the first one is not a S of club, what is the probability that the second one is a S of club? You can multiply it by the probability that the first one is not a S of club, and when you simplify that, you will get the value 1 over 52. So, but your reasoning is exactly correct. That is the reason for that practical reason. Right. Okay, let's look at this one. A coin is tossed 6 times. Two possible sequences are given like this: H T T H T. The coin must land H O T in the order given. Which of the following is correct? Sequence 1 is more likely, sequence 2 is more likely, both are equally likely.
Third.
Third one. Right. Under some assumption. What is the assumption?